Hello guys, welcome to high school physics, and today we are going to be looking at conduction, convection and radiation. So here we go. Right, lovely little topic this one. We can wrap this up pretty quickly, I hope. And let's start by asking if anyone's got a birthday today, and if you have, a happy birthday to you. Okay, and to celebrate your birthday, look at this, your own little birthday cake. All right, fantastic. All right, I'm assuming you're not 1 year old, but hey, you might be. And conduction, convection, radiation. Here we go. All right, and it's nice to celebrate it with a cake. So a quick introduction to these three ways of transferring heat or transferring energy. Okay, so you've all heard of conduction, convection and radiation. All right, and let's look at conduction to start with. Okay, now conduction, we need a medium, and the heat needs to pass through our medium. So I'm just going to move that a little bit. There we go. So we need to put our heat through a medium for conduction. Okay, and to do that, we can use a piece of metal. So here's a nice spiky piece of metal. Okay, and I just took it off a barbecue the other day. My barbecue broke and I just couldn't resist saving one part of it, and already it's coming in use. So conduction needs a medium to go through. It's usually a metal, because metals have lots of electrons. And if we hold this piece of metal here, okay, there's our lovely piece of metal fresh off the old barbecue. Okay, then we put our metal in the flame, and if you look at the dial carefully, all right, you will see the temperature is rising. Okay, so have a little look at that red arrow, that red needle. Okay, might not be too clear, so let's come in. Okay, there it goes. All right, let's move that around a bit more. Okay, so temperature's way up there to 100. Now, what you would have noticed is the temperature keeps rising even when we're out of the flame. Okay, so it's taken a while for the heat to travel through the metal. All right, it is taking a while for the heat to measure to travel through the metal, and it's just creeping up a little bit there. Okay, so that's conduction. For conduction, we need a medium. Metals are very good, because conduction works by the vibration of the lattices. Now, the lattice are the molecules or the atoms inside. They vibrate, they make the electrons vibrate. There are so many electrons in there. We call it a sea of electrons. Like if you had a lot of water, you'd call it the sea or the ocean. Well, we call it a sea of electrons. The lattices vibrate. Those vibrations are passed on to the electrons, and that transfers our internal energy, and the heat is conducted through it. Conduction works well. Thermal conduction usually works very well in the same products or the same things as electrical conduction, but it's a different type of process, but they both rely on electrons. Okay, so conduction, pretty straightforward. Yeah, liquids don't tend to be good conductors, but they can be. Mercury is a good conductor, but it is a metal, so you would expect it. Okay, water is a poor conductor, but is a good convector. Okay, so convection. Easiest way to show convection is to use a joss stick, okay, and make some smoke. And guys, it doesn't take much more than that, does it? Okay. By the way, thank you for celebrating your birthday with us. And okay, the smoke rises. That's it. We can see the smoke rising there, and there's no surprises that that's our conduction, convection. All right, and we tend to say hot air rises, and we can see that with the smoke. All right, now in truth, the hot air isn't rising. I know we do say it. We do tell you lots of little porcupines, all right, in physics, and later on you'll find out that wasn't quite true. Yeah, so we do tend to simplify things. We do say hot air rises when you're younger, but you can see the smoke does rise. It is taken up in the hot air. All right, I don't deny that at all. I just need to, it's a good smell, guys. I just need to extinguish that in my tea. There we go. So I'm just going to kill that flame. And the hot air does rise, but really what happens is the hot air expands, right? When the air is heated, it expands, it becomes less dense, and the colder air around it pushes it up. Okay, so we do say it rises. It's like a vacuum cleaner. We say a vacuum cleaner sucks things in. Well, actually, the vacuum cleaner makes a lower pressure inside, and the stuff is pushed into the vacuum cleaner. All right, it should be called a pusher cleaner because the stuff is pushed inside because it's got a higher pressure outside than inside. And with the air or a fluid, it can be a liquid. If the water, say, is heated at the bottom of a saucepan, it expands, it becomes less dense, and it is pushed up by the more dense fluid around it. Okay, that's convection. All right, conduction, convection. Yeah, convection works very, very well in liquids and gases, which we call fluids, conduction, great in solids, because guys, you can't move a piece of that solid through the rest of the solid, can you? Good point. Okay, last thing, radiation. Okay, so radiation is just feeling the warmth around something. Okay, I hold my hands here around your lovely birthday cake. Okay, and I can feel the warmth and it's coming out. Okay, in all directions. The candle is radiating heat. Okay, the candle is radiating heat. The heat, I can feel it down here. I can feel it to the sides. I can feel it around here. I'm not feeling the heat from convection because that's up here. That is very warm. I'm not feeling the heat through conduction, very similar to the light. Now, light is part of the electromagnetic spectrum, and heat is infrared. Infrared is heat, and that's being radiated the same as the light is. Okay, they're all part of the same spectrum. You know, red, orange, yellow, green, blue, indigo, violet. Well, next to violet, if we squash the waves up a bit, we turn it into ultraviolet. Yeah, and if we're at the other end of the spectrum next to red, you can stretch those waves out a bit and turn them into infrared. Well, that's heat. It travels at the speed of light because it's almost the same as light, just got a slightly longer wavelength. Okay, and it radiates in all directions. And what do you know about light? Light does not need a medium to travel through. How do we know this? Because the sun is 92 million miles away and we get sunlight to Earth, and between us and the sun there isn't much going on. There's kind of a couple of big rocks and a little bit of atmosphere. Okay, and the rest of it is nothingness. Yeah, so heat and light do not need a medium to travel through. Okay, so that's radiation. I am just about to go happy birthday to you. Okay, so what else we're going to talk about? Well, other little things to mention are, let's take a look at our list. Here we are. I'm just going to switch the screens around, guys. Bear with me. And ka-ching, there we go. All right. Conduction relies upon lattice vibrations and electrons. So the lattices vibrate, they make the electrons move, and that transfers the heat along. Okay. Conduction is there. Next is convection. Convection. With convection, this relies upon DC density changes. Okay, so we no longer say the hot air rises, we say that the movement, whether it's smoke or water, whatever's happening, is happening because it is being, let's go back into focus, guys, it's being pushed up. There's a push due to density changes. Yes, that is an N. Well spotted, those guys. Okay, and radiation is part of the EM spectrum, electromagnetic spectrum. All right, now that includes radio waves, microwaves, infrared, visible, ultraviolet, X-rays, gamma rays. They're all part of the big spectrum. We've got the little spectrum, which is visible light. And then we have the great big spectrum, which is all of the things. They all travel at the speed of light, 3 times 10 to the 8 meters per second. Okay, 3 times 10 to the 8 meters per second, which means if you were to send a beam of light around the world, okay, and it wasn't being slowed down at all, it wasn't in a piece of glass going slower, but if you could send something around the world at the speed of light, it would go around the world 7.5 times in a second. And that's why we don't travel at the speed of light, because you can never stop at the right place. Yeah, if it goes 7.5 times in a second around the world, by the time you start the engine and stop, you've probably missed your destination. Okay, that's the only reason we don't travel at the speed of light. I might be lying. Okay, so that's the EM spectrum, and radiation is part of that. Now, guys, conduction, there's 2 conductions: electrical conduction, thermal conduction. Radiation, this is thermal radiation, not the other one. Yeah, not nuclear radiation. We do this on purpose so people fail physics, all right, to make it confusing. So don't be confused by the different conductions and the different radiations, all right? So finally, down here, L is for Leslie. And good old Leslie, he had this cube, all right? And a Leslie's cube is a great bit of kit. Let's just have a little flick around here and change things. Leslie's cube is a great bit of kit, and what it is, it's about yo big, okay? And it's got different textured surfaces, different colored surfaces. Some of the surfaces, one is white, one is black, one is shiny, one is dull, one is black and shiny, one is silvery and shiny. So it's got all these different surfaces. And what you do is you get your metal cube, you pour some water in it, nice hot water, and you measure the temperature. You can just use a little, zippy zappy temperature probe, and just measure the temperature. Different surfaces give out heat at different rates, okay? Shiny, smooth surfaces do not absorb heat well and do not give out heat well, okay? If something is white or shiny, it doesn't absorb heat too well and it doesn't give out heat too well. It doesn't radiate heat, right? A black object, you will know this, guys, if you sat on hot car seats, which are black seats, they get very hot, okay? Black absorbs heat well, and black emits heat well. So if you've got a black house, some people paint their houses black, then it heats up in the summer, it gets very, very hot, which is not very comfortable. And in the winter, it will lose heat quicker because it's black. White houses, smart idea, guys, not only reflect the sunlight in the summer, but also they emit less heat in the winter, okay? So that's something to think about, all right? And the texture also helps. If something is dull or rough, but dull in particular, then it will actually radiate heat better, okay? And if the surface temperature is higher, obviously it's going to give out more heat, all right? So that's radiation. And good old Leslie's cube is a way of looking at that, because all those different faces on the cube will all have the same temperature internally, but they emit the heat at a different rate. Polar bears, let's mention a bit of biology. Polar bears are white, but their skin is black. Okay, a polar bear has black skin. Now, the white fur on a polar bear is actually transparent. When you look at the end of it, you can actually see through the hair. I don't advise, you don't go up to a polar bear and just go, look at that. Okay, so when you look through the hair on a polar bear, it's like an optical fiber. Yeah, the sunlight travels down inside the fur, hits the black skin and gets absorbed. Yeah, so that the polar bear can warm up nicely. All right, using the sunlight. Good point. Okay, right. What else do we need to mention? I'm just having a quick look over at my notes. And I think, guys, we have pretty much covered everything. One way to remember the difference between conduction, convection, radiation is to think of that amazingly cool sport, like the best sport on the planet, okay? Good old ultimate frisbee, okay, guys? And if there's any ultimate frisbee players out there, you know what I'm talking about, okay? If you want to think about conduction, if this was our packet of heat, conduction would be, we flick the frisbee around to every team member, ting, 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 every team member. Yeah, the packet of heat goes from player to player to player. And then eventually we get to the end, yes, and we get that point, okay? Now, radiation would be that long shot, okay? If someone's in the end zone and you're going to send that packet of energy straight to them, all right? That's radiation, all right? You're going to get that lovely hammer throw in, whoosh, okay? And off it goes to the end zone. All right, that's radiation. Now, convection doesn't work with our frisbee routine, guys, because convection would be you pick the disc up and run with it, okay, which we don't do in ultimate frisbee. So you'd have to revert to a game like football, okay, or rugby, whatever you're going to be playing, and same old thing. The rugby ball goes from player to player to player. That's conduction, okay. The big kick, woof, that's radiation. But if somebody picks the ball up, almost dropped it, and runs with it, that's like convection, okay? Because the body is carrying, the fluid is carrying that packet of heat with them, all right? So you can use a little bit of sport to remember conduction, convection, and radiation. Now, to finish off with, I could have a little bit of your birthday cake. So good. And, have we covered everything? We have. So, if you haven't played ultimate frisbee, homework is to get out there and play ultimate frisbee. Probably the coolest sport ever invented. Okay, guys, I'll see you later. Thank you for joining me and see you next time. Goodbye.